everyone! Welcome back to the channel. Today, we're diving into something really cool, graph book embedding. Have you ever wondered how we can neatly organize a graph inside a book with multiple pages while keeping the edges from crossing? Well, that's exactly what graph book embedding is all about. In this video, I'll break it down for you, what it is, why it matters, and of course, show you some interesting examples. So, if you're ready to explore the pages of this mathematical concept, let's jump right in. Now, you might be wondering, why does graph theory have something called book embedding? Well, let me break it down for you. Graph theory deals with networks of connections, whether it's social networks, circuit layouts, or even DNA structures. But sometimes, these connections can get really messy, with edges crossing all over the place. To make sense of this chaos, mathematicians came up with a clever way to organize graphs neatly by embedding them into a book format. In this concept, all the vertices are placed along the book's spine, like a single row of dots. The edges are drawn across different pages so that no two edges cross on the same page. The goal? To minimize the number of pages needed while keeping everything organized and readable. So instead of a tangled mess, we get a structured, layered representation of the graph. Book embedding isn't just a fun puzzle, it's a crucial tool for solving real-world problems. In fact, this concept plays a huge role in several important fields where organizing connections efficiently is key. Let's take a look at some examples. 1. Circuit design. When designing microchips, we need to avoid wire crossings, just like separating edges in a book. 2. Parallel computing. Storing and processing large data structures efficiently follows book embedding principles. And 3. Bioinformatics. Scientists use graph structures to analyze DNA sequences in a structured way. At its core, book embedding helps us simplify complexity. Instead of dealing with chaotic graphs, we structure them in a way that's easy to analyze and compute. Alright, now that we understand what book embedding is, let's apply it to a real-world problem. Train scheduling at a busy station. Imagine we have a train route connecting 5 cities, X1, X2, X3, X4, and X5. The train departs from X1 to X5, making stops along the way. If we represent this as a graph, each city is a vertex and each direct train route is an edge. Since every city is connected to every other city, this forms a complete graph K5. Now, here's the problem. If we try to draw this network on a single page, we'll end up with a lot of overlapping routes. That's where book embedding helps. Instead of having messy, tangled tracks, we distribute them across multiple pages or layers of organization to prevent crossings. Alright, now let's go step by step and see how we can embed the train route network into a book using graph book embedding principles. Step 1. Placing the stations along the book's spine. First, we need to arrange our 5 stations, X1, X2, X3, X4, and X5, in a straight line along the book's spine. This means that each city is placed in a fixed order, just like words in the binding of a book. Imagine drawing a vertical line. This represents the spine of our book. Now, we place our 5 stations along this spine, like this: X1, X2, X3, X4, and X5. This step ensures that all train routes will originate from or pass through this central reference. Step 2. Connecting every station to form the K5 graph. Since this is a complete graph K5, every station is directly connected to every other station. That means each city has a direct train route to the 4 other cities. Connections in K5 equals X1 is connected to X2, X3, X4, and X5. X2 is connected to X1, X3, X4, and X5. X3 is connected to X1, X2, X4, and X5. X4 is connected to X1, X2, X3, and X5. X5 is connected to X1, X2, X3, and X4. If we try to draw all these connections on a single page, it becomes a tangled mess with edges crossing everywhere. That's why we need to distribute these connections across multiple pages. Step 3. Assigning train routes to separate pages. Now comes the critical part, placing edges, train routes, into separate pages to eliminate crossings on the same page. How many pages do we need? Mathematically, a K5 graph requires a minimum of 3 pages for a proper book embedding. Let's assign the edges strategically across these 3 pages. Page 1. Assign edges that connect x1, x1 to x2, x1 to x3, x1 to x4, and x1 to x5. Flip to page 2. Page 2. Assign edges that connect x2 and x3, x2 to x3, x2 to x4, x2 to x5, and x3 to x4. And flip to page 3. Page 3. Assign remaining edges to x4 and x5, x3 to x5, and x4 to x5. By distributing the edges like this, we make sure that no 2 edges cross on the same page. Each page contains only a subset of connections, keeping everything clean and organized. In a real railway system, this approach helps to schedule train departures efficiently. Each page could represent different train lines or time slots, preventing congestion and confusion in the scheduling process. And that's how we embed a train route system in a book using graph book embedding. By organizing stations along a spine and distributing train connections across multiple pages, we turn a chaotic system into a structured, efficient model. I hope this video gave you a fun and clear look into how graph book embedding works and why it actually matters, even beyond math theory. If you enjoyed this explanation, don't forget to like, subscribe, and hit that notification bell so you won't miss out. Until next time, keep exploring, stay curious, and thanks for watching, everyone.